something up here? Will be much easier with slides. Right, okay, so when I talk to people about what I do in my work on the Great Barrier Reef, the most common question I get is it really as bad as what they say? And people are naturally very curious about how climate change is affecting corals. But more than just understanding the demise of corals, they're very interested in also hearing whether there's anything we can do to help them through this bottleneck. And they want to also know, are we really at that stage where active intervention is the only option? So what I'd like to do today is to take you on a little bit of a journey of how I got to this place. Then I'll go through some of the possible solutions that we're exploring at the moment to see whether we can help corals become more temperature tolerant. And then I'll end up addressing the question, are we really there yet? So I actually got scooped by the primary school student this morning. I was not happy about that. She described her first experience with a coral reef, and I have to say that my experience was exactly the same. I left Denmark when I was a young adult on the looking for adventure and wilderness in the world, and I went to the Maldives. This was the first place that I ever snorkeled, and I was absolutely blown away by the colour, the diversity of form and function. And that initial amazement soon turned into curiosity. I was very curious about how this system worked. And I thought that with knowledge and an understanding of coral reefs, surely we could protect them for the future. Now, I wasn't the only person with that idea. Since about that point in time, we have actually published over 10,000 papers with coral reef in the title. And I have undertaken my education in coral reef science, and during that time I have learned that corals are indeed not slimy rocks. They are very complex and fascinating animals. They live in symbiosis with algae and microbes that affect their temperature tolerance and their health. But not only are they fascinating animals, they're actually also individuals, and they're hugely variable in how they respond to stress. They're variable both at the phenotypic level and also at their level of their genes. And this is really important because variations, standing genetic variation, is the fuel for adaptation. We've also learned that corals tend to pass their traits off to their offspring. So a trait like temperature tolerance is heritable. More temperature tolerant parents tend to have more temperature tolerant babies. And we've learned that this variation is not randomly distributed across space. So corals are locally adapted, they tune to their local environments, and we can see variation in coral populations depending on those environmental conditions that prevail where they live. But this knowledge has not protected reefs from the effects of climate change. Here's a picture taken from the Maldives, where I dove the first time in 2016 during the global bleaching event. What we know is that corals are very sensitive to temperature rises, and it only takes about 1 to 2 months of 1 degree above the long-term average, the long-term high temperatures to bleach a coral. And so I found myself not studying what makes coral reefs thrive and grow and be healthy, but actually recording what is killing them. So here's a picture from the formerly splendid reef off the coast of Townsville that experienced quite significant bleaching in 2017 and was also at the receiving end of the crown of thorn outbreak. And so what I found myself part of was a group of people looking at how coral reefs had been affected by these bleaching events. And in fact, we believe published estimates, and what I've been able to gather from the media is that maybe up to about 50% of the corals we had left died in that short period of time. And so this was really a wake-up call for me. It was a matter of facing the fact that we are living in a warming future, and perhaps we need to apply the knowledge that we have and the understanding of coral reefs in a slightly different way to try and find new solutions moving into the future. And so in the Reef Restoration and Adaptation Program, as David has just outlined to you, we are looking at exploring the feasibility, the benefits and the costs and the risks of a range of new additional tools for reef management. And what I'm focusing on in this talk are just the tools that are aimed at enhancing the temperature tolerance of corals. So what we're looking at is whether we can use naturally occurring evolutionary adaptive mechanisms and gently nudge those processes to help corals become more temperature tolerant. So we're exploring a range of different techniques ranging from trying to identify and proliferate the natural winners, so the temperature tolerant corals already out there in the system. Whether we can use conditioning where we expose corals to sublethal levels of stress and thereby build their tolerance. Whether we can develop probiotics, whether in the form of prokaryotes or algae, for corals so that they can associate with more temperature tolerant partners and in that way increase their resistance to heat. We're looking at whether we can hybridize coral species, so bringing together the genetic material of two different species to form what's called hybrid vigor, or a vigor of these offspring. We're also looking at whether genetic engineering techniques can be used. So these are most commonly aim to either insert or delete a gene from the genetic material of organisms. And lastly, I will say we're not considering this for the Great Barrier Reef at the moment, but it could be a possibility in the future to actually import corals from warmer reefs around the world. So if we're looking at the natural winners for starters, I told you a minute ago that corals are locally adapted. And I'm also going to tell you now that temperatures vary quite dramatically across the length of the Great Barrier Reef, even within reef systems. And what this means is that corals on naturally warmer reefs tend to have a higher temperature tolerance than those on the cooler reefs. And perhaps we can encourage the dispersal from those warmer to cooler but warming reefs. We're also exploring the possibility of using natural survivors from bleaching events, from the bleaching events that we've just seen. So these are hypothesized to be the strong ones out there in the system. Could we proliferate them on the Great Barrier Reef, potentially through fragmentation or breeding in the laboratory or aquaculture facilities? And lastly, we're looking at whether we can actually develop genetic markers of tolerance, so we can go to the reef and identify those individuals that are naturally tolerant. I want to share this photograph with you over here. These three individuals of one species were kept in the lab where they received over 12-degree heating weeks. So this was quite an extreme heat stress. And you can see that just one of them here is actually completely fine. There is standing genetic variation for temperature tolerance already present on the Great Barrier Reef. The trick is going to be finding it. We have specialist talks about all these three topics in the session tomorrow afternoon, so I encourage you to come along to hear more. We've explored a number of other approaches in the lab, and we've actually got very promising results. So we've found that training or conditioning down here helps. We can elevate the tolerance of coral larvae by just exposing them to hot water for a couple of weeks. Neil Canton is going to give a talk tomorrow again about a longer-term experiment that is looking into whether conditioning can enhance the performance of corals under future climates. We've got very promising results in terms of hybrid vigor, where the hybrids of two sets of Acropora species both grew better and had higher survival under future temperatures than under ambient. And research again out of Madeleine van Oppen's group have found that we can select for more temperature tolerant algae in the lab, but the key here is that the symbiosis is the tricky part. Feeding that back into the corals and getting them to still play nicely with these new partners is a little bit more difficult. In terms of genetic engineering, I will say that we are at the very start of this journey. We've had just one paper in this area providing a proof of concept that using these techniques that have really only been on the playing field for about 5 to 6 years can be applied to corals. This is not being proposed on the Great Barrier Reef, but it has certainly been in the literature that perhaps by taking corals from much warmer ocean basins, the Red Sea or perhaps the Persian Gulf, through cryopreservation, you could actually integrate that tolerance into corals on the Great Barrier Reef. So our research at AIMS and with our partners around the world have shown that it is certainly quite possible for corals to gain 1 to 2 degrees in temperature tolerance. And we can speed that process up and promote that process through the approaches that I've talked about. But is this going to be enough? Is this a silver bullet for coral reefs? Well, I will say definitely not. We need to consider the future climates, and whatever that pans out to be in 2050 is very much going to govern the success of these sorts of approaches. So if we pull up on the Paris Agreement and we keep warming to 1.5 or maybe 2 degrees, I think that many of these approaches have real legs. If the oceans will warm further than that, then we need to do a lot more development. But as it's been said and mentioned a few times, none of these interventions are without risks. They all carry risk, and for the most part, these risks are just discussed at academic at the moment. They have not been tested in the wild yet, and so there's a lot of work to be done to understand them and to evaluate whether they are in fact acceptable to us and to the Australian people and indeed to the world. The risks mostly group into areas around disrupting local adaptation. So if corals are adapted to all sorts of conditions, not just temperatures, by introducing corals into these environments, you might disrupt those local patterns. There's risks about disrupting the health of corals and also trade-offs in terms of temperature tolerance or growth. So we need to be very aware of those. There's issues surrounding genetics, not only by promoting temperature tolerance in a smaller stock, but also through the production, the aquaculture production, and potentially also the deployment phases. So the last thing we want to do is to create artificial genetic bottlenecks in our coral populations. And so what we have to do here, I think, is look very closely to our friends and colleagues in the aquaculture sector that have gone through a lot of these issues already, and that can give us tips and guidelines about how we best approach selection for increased tolerance, but also aquaculture production of these corals. Whoopsie, that was not on purpose. And obviously one of the major risks associated with introducing either individuals or species onto reefs that were not there in the first place is the risk of invasiveness. The scale of the Great Barrier Reef is often cited as a major barrier for the development of these tools, but it can also be an opportunity. It's clear that we need to prioritise and we need to optimise the methods. We cannot work on 450 species of hard corals, but we can identify those species that are most important for ecological function, or those species that support the values that people place on reefs. Not only do we need to prioritise and optimise in terms of doing what we know how to do better, but I think we need to innovate. We need to start doing things in a completely new way. And I take great heart when I hear the story of the human genome. I think very few people would argue that that has not been a major undertaking and a major victory for humanity. In fact, that program was running behind schedule and over budget for about 80 to 90% of that project until there was a step change innovation in sequencing technology that allowed the entire genome to be pretty much sequenced in the last year of the project. So while we can't hang our hat on innovation, I think we should approach that with very open arms because that could be the step change that we need in terms of being able to implement some of these approaches at scale and at cost. So what's next for us? Sorry, David, I didn't look at you, I didn't frown at you earlier this morning, but I do think that we need to be courageous enough to move some of these studies out of the lab and into the field. There's no guarantee that the performance of a coral in a sheltered laboratory environment is going to be the same in the wild. And so I think we need to work with our managers to develop risk-acceptable approaches where we can remove all this material if it's not appropriate, but still allowing us an opportunity to examine this on the reef where it really matters. We need to learn a lot more about the genetics of corals, not only what underpins their temperature tolerance and their health, but also the production and deployment of corals. And we need to innovate and we need to collaborate, as has already been emphasised today. So, are we there yet? Anyone with children will know that that starts actually when you first leave your house. Are we really at a stage where active, radical, potentially intervention on coral reefs is our only option? Well, I say no, absolutely not. But the time to start the research is now. We need time to evaluate the cost, the benefits, and the risks of all these approaches. We need time to start the conversations with all stakeholders so that we can find common ground. And with that, I will say thank you to my team at AIMS and in RRAP. I'm very happy to be sharing this knowledge with you today. I will say that if you want details, if you want to see some graphs, come to our session tomorrow afternoon. I've told you about my journey. I'm very open to hearing about yours and starting a dialogue around this.